Consider the wind turbine. It's probably one of the few truly clean and sustainable energy sources in our lives. It's the product that can power our world for generations to come. With this unique relationship the wind turbine has with our future, we take changing it really seriously. We don't want to just make a new wind turbine. We want to make a much better wind turbine. The Shroom is the result of this approach. It's been completely rethought, and for the first time ever, we have increased the size of the nose cone. By making the nose bigger, not smaller, you can harness more of the wind energy while maintaining the overall dimensions of the wind turbine. And yet, even with the larger nose, the Shroom is one of the lightest wind turbines we have ever built.
To achieve this innovation, we had to re-examine every component. It took an incredible collaborative effort to do this. From the beginning, we knew we wanted a bit different. While others are making their nose cones smaller, we've made ours bigger. 6 times bigger than anyone else.
What the bigger nose does is it enables airflow that often neglected and wasted through the center of the wind turbine to be harnessed for greater power generation. By covering the blade roots, the bigger nose cone deflects air that would have normally flowed past the roots to the outer span of the blade. The wind turbine will experience an increase in mass flow over the outer span of the blades. It can potentially deliver more torque and hence more power to the generator. Given the dimension of the new nose cone, we needed to manage mass very carefully. We have created an all-new, much lighter, hollow nose design. Using 3D printing technology allows the wall to be thinner and more durable. I don't think the level of innovation has ever been matched by any other product we have created. The bulk of the power generation still lies in the blade. The SG6040 to SG6043 series of airfoils has been optimized for small, horizontal wind turbines. It will be almost foolish to consider anything else. We like the SG6043 airfoil, especially in the way it delivers the highest lift coefficient and yielded enhanced lift-to-drag performance. For maximum power generation, careful design goes into ensuring the blades maintain its optimal angle of attack, even under high air load. By thickening the SG6043 airfoil by 11.5%, we have achieved a 30% reduction in blade deflection, with only a slight compromise in aerodynamic performance. The seamless integration between the hub and the blade is achieved by blending the airfoil into an almost circular route. This allows the blade to withstand high centrifugal forces while further reducing blade deflections. Using MATLAB and the all-important BETS equation, we have created a blade that can deliver high power output at a design TSR of 4.5.
We had one thing in mind when we designed our blades: performance. Getting inspiration from the aircraft wing, we've added winglets to our blades.
The winglets, which we have made to be about 3% of the turbine radius, are designed to recover some of the energy in the blade tip vortex to improve the performance of the blades. This effect is similar to increasing the effective aspect ratio, producing an especially good performance boost by reducing drag.
Now, picture our winglets seamlessly blended into our twisted blades. It looks amazing.
When it comes to manufacturing the aluminum hub, 4 processes were involved: turning, milling, drilling and broaching. Firstly, turning was used to reduce the diameter of the aluminum piece to the size of the hexagonal hub. The same process was then used to create a center hole for the shaft. Thereafter, the designed hexagonal shape was achieved using milling, whereby 6 flat surfaces were created around the circular hub. Having produced the designed shape in size, the hub was drilled for smaller holes so as to minimize mass. Finally, the keyway was broached, and with this, our hub was completed. Meanwhile, the blade and the nose cone were manufactured using a rapid prototyping machine, which were then sanded using increasingly fine grades of sandpaper to achieve smoother finish.
Having manufactured our turbine, we finally had the opportunity to test it in the Donald Campbell wind tunnel. At 103 grams, it is very close to our approximated mass of 95 grams. The turbine was connected to a shaft and a hysteresis braking system. It was tested at various wind speeds from 6 meters per second to 12 meters per second, with the torque and the RPM measured by the torque transducer. Our wind turbine failed to self-start at 10 meters per second, and this was no surprise to us considering the size of the manufactured wind turbine. During testing, the turbine was allowed to reach its maximum RPM at the tested speed. The brakes were then applied for a gradual deceleration to find the maximum CP and the respective TSR. From the plots, it is clear that the blades perform better at higher wind speed with maximum CP of 0.164 at 12 meters per second. The TSR at this wind speed for max CP was 4.9, which was slightly higher by 0.4 units from our initial design TSR, a TSR of 4.5. This difference is due to the assumption of lack of viscosity. Furthermore, a loud noise was heard when tested at 12 meters per second, which could be due to the resonance of the turbine blades. Although testing at 6 meters per second was difficult due to stall, we managed to get a few data points corresponding to the very narrow range of RPM. We also tested our wind turbine without the nose. Unlike the original blade, the noseless blade stalled before any readings could be taken at 6 meters per second. This could mean that our nose had a significant effect of deflecting the flow along the wingspan at lower speed, enabling the turbine to generate more power. At higher velocity, the blade without the nose performed almost as well as our original blade. The max CP of 12 meters per second was 0.158 in comparison to 0.164 for the original blade, translating to a 3.7% difference. The tip of the noseless turbine was then sanded to remove our winglets. Again, no data was obtained at 6 meters per second as the blade stalled. As the speed was increased, the power generated was notably lower than our original blade. At 12 meters per second, the maximum power generated did not cross the 20 watts mark as observed for the previous two testing, and was calculated to be a significant 7.92% lower than our original blade. This is proof that the winglet is successful in improving the performance of the wind turbine.
Our unique design clearly has its advantages. While it is good, we want to make it even better.
The enlarged nose cone has proven its worth at the low speed regime. However, the nose might have resulted in complicated turbulent flow near the blade root at high speed, increasing wake production losses and limiting the maximum power achievable. An extended shielding design could allow the flow to be diverted smoothly onto the blade, thereby reducing the strength of the wake. A more refined blending of the blade into a circular root section will also reduce the deflection of the blade during rotation, allowing it to spin closer to the optimal angle of attack for maximum power generation.
Power generation of the wind turbine can be further enhanced with an improved blade design. Our original design was made to thicken the SG6043L4 section by 11.5% to increase the structural strength of the blade. This in turn compromised the performance of the L4 section. Using the original SG6043 section will optimize the performance of the blade. The use of the winglet on the turbine blade is still at its infancy. However, our initial design has proven it does help improve the power. Our conservative approach to design has limited the size of the winglet. Further trials can be carried out to refine the dimension of the winglet for further performance. A thinner cone would be possible with a more precise 3D printer, and a smaller hub section can be used to further reduce the weight. An estimated 30% weight savings can be achieved with the two suggested areas. Through the implementation of the above improvements, we are certain that we can produce a much better wind turbine, competing with the best on the market. To create the shroom, we began with a design that we really loved, but to build it, to implement it, we had to look far beyond what we knew to be possible. It took all of our learning, our best thinking, to realize something so simple, so pure, and yet so truly extraordinary.